A and B. Let's redo the exact same problem, but now we're going to put friction on the table. That is that you're going to be given MA, you're going to be given MB, and you're going to be given mu K and mu S. If, for example, you're being asked, what is the acceleration of the system? That's what I meant, Kalia, by saying I will, on the test, not on the quiz, I will never try to trick you. If I'm asking you to calculate the magnitude of an acceleration, you can assume that the acceleration is not zero. Therefore, that the whole system is moving. Hence, if the system is moving, you not only know you can use Newton's second law because you're looking for the acceleration, but you also know that you're dealing with Fk. If you also know the direction of motion, which in this case is very clear, it can only be that way. We've never been able to observe an Atwood system where B was going up and A was going left. Then you not only know its magnitude, mu Kn, but you also know its direction. Gotta be left. Okay? So just by thinking of the problem and look at what's given to us or what is being asked, if it's moving, very, very easy. You know everything about the kinetic friction. Oof, I love your question, Ray. I love your questions. No and yes, it depends where. So, in the entire class, you will always be told that the pulley is frictionless. Okay? What they mean by that is there are two places where the pulley may experience friction. Here, on the rim, between the string and the rim of the pulley, and on the axle. Those are the two possible places where friction may be present. When in this class, whatever book you're using is telling you that the pulley is massless and frictionless. Massless keywords tells you as usual the tension is the same. Frictionless refers to the axle only. Okay? It doesn't refer to the rim. You have to have friction on the rim because otherwise the string would slip. Okay? We're not dealing with this case. You're going to be dealing with this case in C270. You're going to see that there is an exponential between T1 and T2. And this exponential depends on this angle, which represents the angular amount, so the amount of wrapping that is around it. Okay, so in this class, when they say frictionless pulley, they always refer to the axle. Of course, there is friction on the rim. We have to have friction. This class requires friction on the rim. This class always satisfies the no slipping condition. So there is no slipping between the string and the rim of the pulley, which implies that there must be friction. And we don't care about that friction. We never will. When they say frictionless pulley, they always refer to the friction on the axle. Thank you for asking that question. Oh, so is the rim friction always static or it slips? Aha! Well, if there is no slipping on the rim, then the type of friction present gotta be static. And sure enough, I believe there is a mu s in there. If there is slipping between the cord or the string and the rim of the pulley, then we're going to have to deal with kinetic friction. So same concept. But this will only show up at the end of C270, the last chapter. Okay? Good question, John. Never. The mass of the string will be considered in Physics 310. And for this, you're not going to use Newton anymore. You're going to go, screw Newton. You're going to use another method called the Lagrangian. Much more powerful. So that's just going to be another model, another story that you're going to use, another bunch of characters that you're going to be allowing to play, allow them to play with each other so they can describe, let's say, a rope that is falling down. Let's calculate the velocity of the end of the rope as a vertical rope is being dropped. If you try to use Newton for this, woohoo, good luck. I see you in a couple of days. But with the Lagrangian, bing, bang, boom, a couple of hours, not even. Okay? Lagrangian is not going to be part of this class until we reach oscillation. I will mention it, but it's very, very similar to energy. So we'll see that. We'll touch upon it just for good karma towards the end. Okay, so everybody's clear about the friction on the pulley, where it is, which one we consider, which one we ignore, which one is relevant, which was not relevant? Everything okay? Which part is not clear? So let me summarize. In this class, frictionless pulley always refer and only refer to the pulley on the axle. So they assume that there is no friction on the axle. So no heat is being generated, no loss of acceleration is being generated. That's all they mean, always. They do not refer to the friction between the string and the rim. Because for this type of problem, for us to be able to analyze it, there gotta be friction between the cord and the rim. Okay, so in this class, we're always going to be dealing with no slipping, which refers to this type of friction. And yet, we're never going to have to go in detail into trying to figure it out. We're going to go around it and use it at our advantage using a different story, a different model. So we're never going to be concerned about this. You're going to be concerned about the slipping in C271. That's where, shit is going to hit the fan and it's going to be a little bit more complicated. So all the equations you're going to see in this class, you're going to have to add 1, 2, 3, 4 terms to handle the slipping. Of course, Ray, absolutely. That's why I kept saying the assumption that we make is that the pulley is massless, which therefore allows us to simplify our problem and to equate T1 and T2. But you're absolutely right. T1 is never equal to T2. But we're only going to introduce this case and make it a little bit more realistic in chapter 10. And then you're going to make it even more realistic in C271 and 270 by looking at the amount of wrapping on the rim. Okay? Excellent. So is that better, Drew? Frictionless pulley means no friction on the axle. That's it. They do not refer to the friction between the string and the rim. That's all. Excellent. Okay, so what were we doing? We're doing Atwood, and we figure out that first we're dealing with FK because we're looking for an acceleration, therefore the bugger is moving. And we know that A moves towards the right, therefore it's not only FK, but we also know that FK goes opposite to the direction of motion by this property, therefore FK is going to be left. That's it. So let's do B real fast. We've done it many times before. Weight, tension. Now let's do A. Same as before. Weight, normal, tension, and now the new force, Fk. And I'm going to put mu Kn directly, so I don't have to introduce another equation. That's it. That's the only new thing. Here again, we use the fact that the mass of the pulley is not given, therefore our pulley is massless. Therefore, as we use Newton's third law and the property of the pulley, beeping, beeping, done. So now let's complete our free body diagram and pick our coordinate system. B is going down, therefore I'm going to pick X down. And as Ray suggested, we can even forget Y. A is going right, so I'm going to pick Y right and X up. Remember, X and Y are just labeled. So if you pick positive x for one, you don't have to pick positive x for the other. As long as they're both positive, you can code them differently. X, Y, whatever. Okay? So this will give us one equation, mbg minus t is equal to mba. And this bugger, it's trivial. There is no specific angle. They all align along either x or y. So our x equation will give us na minus mag is equal to 0. And our positive y will give us t minus mu kn. And this n is a special n. It will be Na. Na. As you write the functional form of your friction, the normal force associated with that friction is the normal force on that particular surface where the friction is. It sounds trivial right now, but later on, you may have an object that is being squeezed between two surfaces. And if you have friction here and here, then you have to deal with a normal force here and a normal force here. This normal force will be affecting the friction here, and this normal force will be affecting the friction there. So the normal force will be different. So you're going to have to be careful. All right. That's when, Ray, we have to now use all those stupid equations. Before, we didn't need the x equation. We didn't need that one. Now we do. Oh, I'm sorry. Wrong one. We didn't need that one, right? We got away with this one and this one. The problem now is friction is showing up here. That's a new term. And it involves Na. And Na is not here. Na is there. So friction now forces us to go from a 2x2 to a 3x2, 3x3. So we really have to use those three equations. But that's okay. I mean, it's trivial. So obviously we want to solve for Na, substitute it in there, and then add them up again. So mbg minus t plus t minus mu k na, and na is mag, and this is equal to mb a plus ma a. So really, just algebra, just one more stupid term. As you solve for a, mb first minus mu k ma second times g divided by the total inertia, as usual, ma plus mb. Okay? Remember, last time we had the exact same functional form, except the blue term wasn't there. Every time you're going to be dealing with friction, at the end, whether you're going to be doing acceleration or energy, such as velocity, the term that refers to the friction term should always be negative. Friction is a non-conservative force. It will always decrease the magnitude of the acceleration or the velocity. It will always go against it. If you have no friction, you will go faster. So if you include friction analysis, there should always, 100% of the time, 200% of the time, be a negative sign associated with those stupid mu k or stupid mu s.